So what I'll be doing is I will guide you to understand these electric fields better. So let's start. Now, when we say electric fields, what we actually study in electric fields is we study about the forces, fields, and the potential due to charges that is at rest. Okay, this is what we actually study. So here we are studying about charges at rest, and the other fields, the magnetic field, current, electricity, electronics. Here we deal with charges that are in motion. Okay, so here we will be dealing with charges at rest. So objective of today's meeting is to provide you with a big picture of electric field. So let's divide electric field into two parts. First, what we can do is we can say electric fields where we discuss about point charges. Okay, electric fields where we discuss about point charges, and then we have the other types of charges. So in point charges, you might have studied about the Coulomb's law, right? Remember the equation? F is equal to 1 over 4 pi epsilon Q1, Q2 over R squared. This equation. So this equation is only valid for point charges. Okay, if you take point charges, this equation is valid. But for other charges, it is not valid. So first let's look what are the equations we can apply for point charges. Remember this equation? E is equal to 1 over 4 pi epsilon Q over R squared, and V is equal to 1 over 4 pi epsilon Q over R. These equations are only valid for point charges. Okay. For point charges, these equations are valid. Then, what about the other charges? For other charges, we are not able to apply Coulomb's law. We are not able to apply Coulomb's law directly. We are not able to apply it directly. So, what are the examples for other types of charges I'm talking about? For example, you might have studied about charges stored in conducting, non-conducting spheres, right? So you might have studied about charges that are stored in capacitors. And so there are many examples. So all of them are not point charges. So for those types of systems, we are not able to apply Coulomb's law. Is that clear? Just leave a message. How about the others? Now, let's talk a bit about point charges. You know what's a point charge, right? Point charge means it has negligible volume. It has negligible volume. Okay. And it has a charge. Those are point charges. They have negligible volume, but have a charge. So let me mark the forces acting on these two charges, Q1 and Q2, as F1 and F2. What can you tell about them? They are action and reaction pairs. You know the Newton's third law, right? So they are action and reaction pairs. Therefore, they have to be equal. Okay, they have to be equal. And also, the Coulomb's law. F is proportional Q1, Q2, and F is inversely proportional to the separation. So we combine them and we get this relation. F is proportional Q1, Q2 over R squared. So this is the relation that is valid for point charges. That's a very short idea about point charges. Let's try a few questions related to this idea. Shall we try question number 16? Can you just check the question and let me know the answer in the chat? Yes, we have got one answer and it's correct. How about the others? Atifa, you can try the next question. Try question number 21. Others, what do you say? What's the answer? Okay, I'm getting many messages. Those who got the 16th correct can try the 21. Yes, anyone from the boys? Okay, I'm getting answers. Others also try. I will reply. Okay, let's look at question number 16. Um, when we have two charges, plus 1 coulomb, plus 1 coulomb, then we have plus 5 coulomb. So we will have forces on them, right? We will have forces on them. As I mentioned earlier, these are action and reaction pairs. Therefore, irrespective of this charge, both the forces will be equal. Why? Because force is not proportional to a charge. It is actually proportional to product of the charge, Q1, Q2. Okay, so doesn't matter which charge you're looking for. Maybe you're looking at 1 coulomb, but you will have to multiply it with the other charge. So it says it is proportional to the product, not a single charge. Therefore, the answer should be C, 1:1 ratio. Okay. And here, most of the students get confused with larger charge having larger force. That is incorrect, because you have to remember that we need to take the product, okay, not a single charge. Then how about question number 21? Most of you have sent the answers for 21 as well. The others also give a try. And those who got it correct can go for question number 13. And those who have doubts with 21 can listen to me. So question number 21, initially we have plus 2 coulomb and plus 6 coulomb of charge. So they repel each other with 12 newtons. As we mentioned earlier, both of them should be equal, right? Because force depends on the product of the charge. Now, what if I provide minus q charge to this? Minus 2 coulombs. If I provide minus 2 coulombs, now the new charge is 0 coulombs. And the other charge will be plus 4 coulombs. So, as per our discussion, force is proportional to the product, right? So 0 multiplied by 4 is going to be 0. Therefore, the force on each of them is going to be 0. Then it will be answer number A for 21. Question number 13. That's an interesting question. Let's see who can get the answer. So already I got one answer. How about the others? Those who have not replied or dropped any single message can try. #21. Okay. Question number 21. It says, initially we have plus 2 coulombs and then we have plus 6 coulombs. So if I introduce minus 2 coulombs to this, what will be the charge? It will be 0 coulombs. If I introduce minus 2 coulombs, it will be plus 4. Then product, I mean the force is proportional to Q1, Q2. So look, the charge is 0 into 4. You multiply 0 into 4. It is 0, right? I hope that clears the doubt. Okay, question number 13. I have got multiple answers. Question number 13. Some say it is C, some say it is D. Some say it is A. How about the others? I have reacted to those answers. You can check. Okay, most of you are trying. I'll say the answer. Answer is D. Those who didn't get D, try once again and see if you get D. Most of you have got D. Some of you have got A, B, and C. So those who got A, B, and C just can give another try. If your answer changed from some other to D, then also let me know if you got the idea. So let's see. Most of you now got D. So F is proportional Q1, Q2 over R squared. So it says if the distance between the two particles, is reduced to half, so this is half times, and Charge on each particle. Charge on each particle is doubled. So this is 2 times. This is 2 times. Then how many times is the force? These two together, it's 4 times. Then you have 1 over half square. Again, it becomes another 4 times. Therefore, it becomes 16 times. So the answer should be D. Is that clear or need an explanation once again? If anyone still didn't get the idea, the question says the charge, each particle, the charge is doubled. So I double the charge. Okay, I double the charge. And the distance is reduced to half. That means half squared, right? Because it is r squared. If half is squared, then we get 1 by 4. Then the 4 goes to the numerator, then it is multiplied by 4 times. Therefore, 2 into 2, 4, 4 into 4, 16. Then the force is 16 times. 16 times the initial. Got it? Are we clear? Hope the others are also fine. Any other want me to explain it? I hope it's clear. Okay, so next is an easy question. We want to find the electric field strength. Okay, we want to find the electric field strength of a charge. Electric field intensity to the point 20 centimeters away from the charge of 2 into 10 to the minus 5 coulomb is. So you don't need to do it because I have already done it, because I know you all know this equation. So electric field intensity is 1 over 4 pi epsilon naught Q over R squared. If you apply, you get the answer. So did you notice something? Here, we were using the point charge equations. Okay, we were using the point charge equations. But let's see how to get the equation for other types of charges. Okay, so in a question, if you can understand when you read it, you understand that it's a point charge, then you can straight away use it. If it is not, then we will have to go for other options. So that is the basic. Okay. Now this side is clear. This side of the classification, the point charges part is clear. Now what I'm going to do is we are going to go to this side, and that is the important side. So the earlier questions were for you to engage and participate. Now we are going for the important part. Okay, so I hope you will follow along with me. So let's come over here. We came across this symbol, right? Epsilon. What is this in electric field? We know that it is permittivity. Okay, we know it is permittivity. But we have to understand what is permittivity. Okay, let's think this way. Let's think that permittivity means the permission. Okay, just understand. Permission given to the medium to absorb some of the field lines. Okay, so just think that if you have more permittivity, if the medium has more permittivity, that means it has more permission to absorb most of the field lines. Is that clear? Did you get what I'm saying? I hope my screen is visible. The complete screen is visible. So let me show you it using a diagram. Now, let's say we have two charges, Q1 and Q2. Okay, we have two charges, Q1 and Q2. So when they are placed in a free space, so this is a free space, okay? When it is placed in a free space, in that case, so if it is placed in a free space, let's say 100 lines of electric field, okay? We have 100 electric lines of forces. If there are more electric lines of forces, then we know that the attraction between them will be high, right? Attraction between them will be high. Now, we are going to place the same charges. We are going to place the same charges at the same distance, but this time inside a dielectric medium. Okay, we are going to place it inside a dielectric medium. So, what is permittivity? As I mentioned earlier, permittivity is the permission given to the medium to absorb some of the field lines. Okay, so earlier we had 100 field lines, but now look, can you see the diagram? Some of the field lines are absorbed. By whom? By the medium. Okay. Look, some of the field lines are absorbed by the medium. If some of the field lines are absorbed by the medium, then what can you tell about the attraction between these two charges? Do they increase or decrease? Do they increase or decrease? Yes. So if epsilon increases, the permittivity of the medium increases, then the strength of the force or the field will reduce. Okay. If epsilon increase, then strength of the force or the field will reduce. Let's try this question. Question number 9. What happens? It has to decrease, right? It has to decrease because it's absorbing some of the field lines. Okay. Dielectric medium absorbs some of the field lines. Therefore, the force between them reduces. Okay. Now, we have something called the dielectric constant. So this is just like what we have studied earlier. You remember relative density, specific gravity, rho over rho W, something like that. So just like that, what we are going to do is we are going to compare the dielectric or the permittivity of the medium with that of free space. Okay, we are comparing epsilon of medium with epsilon of free space. Then when we compare that, we get something called the relative permittivity. So this is the relative permittivity. Okay, this is the relative permittivity. So relative permittivity has another name, the dielectric constant. Okay. Now you shouldn't get confused with this. Now let's say if they have mentioned in a question as dielectric medium, then it is a insulator. Then they could have used any of them. If they say insulator, then it's a dielectric medium. If they mention it's a dielectric medium, then it is an insulator. Okay. And what about conductors? Conductors, they do not have an epsilon value. Okay, they do not have epsilon value. So if they have given epsilon value, if they have given an epsilon value, then it should be an insulator, then it should be a dielectric medium. Okay. Hope it's clear. So far, is it good? So what we have discussed so far, what I have done is, now we know what are point charges. We know what are point charges, and we know the equations. We know the equations that are valid for point charges. Okay, we know the equations that are valid for point charges. Next, let's see what are the techniques. What are the techniques we can use to obtain equation for electric field, potential, okay, electric field, potential for other charge systems. Let's look how we can obtain the equations for other systems other than point charges. For now, we only know the equation for point charges, right? We have done questions based on that. Okay, so this is the most important part, because the previous one, they are not confusing. They are straightforward. Now we come to the most important part of the electric field, where it starts getting confusing. Now, let's look at the other charge systems. Okay, let's look at the other charge systems. If you want to find the electric field strength, we use something called the Gauss theorem. Okay, we use something called the Gauss theorem. You already know it. And this is the equation for the Gauss theorem. If you want to find the potential, of a system, we use the potential gradient. And this is the equation for potential gradient. So you have to understand what to use when. So let me know, tell me, if you want to find the electric field strength, what is the law we use? If you want to find the electric field strength, what is the law we use? We use the Gauss theorem, okay? And from electric field, once we know the electric field, we can find the potential of that system. So for that, we are using the gradient, okay? So in our syllabus, what are the other systems that we discuss? And for what we need to derive equations for E and V. First one, we have to look conducting solid and hollow sphere. Conducting, okay. Then non-conducting solid and hollow. Then we have conducting slab. We have non-conducting slab. And we have electric field around a wire. So those are the systems that we will have to discuss. Okay, so that's a good question. Electric field strength and electric field intensity, are they same or different? Electric field strength, it is same as electric field intensity. Okay, so both of them are same. Nasif, is it clear? Both of them are the same, okay? So you can, they can ask the electric field strength, or they can ask for the electric field intensity. Okay, so let's understand, how to derive the equation. Now what I'm going to explain is how to derive the equation, okay? I'm going to explain how to derive the equation for other systems. For that, I said we are going to use Gauss theorem. We are going to use Gauss theorem to find electric field strength, and we are going to use potential gradient to find the potential. So for that, we have to understand what is Gauss theorem, right? We have to understand what is Gauss theorem. That is what we are going to discuss next. So what's Gauss theorem? It's very simple. The Gauss theorem says that electric flux is proportional to charge enclosed by the imaginary surface. Now that's very easy. What it says is, now say you have a charge. Let's say we have charge plus Q and plus 2Q. So I have an imaginary surface. What is the flux proportional to? What is flux proportional to? Is the flux proportional to Q or to Q? Is the flux proportional to Q or 2Q or 3Q? What do the others say? Is it proportional to Q, 2Q or 3Q? Now, what about this Gauss surface? By the way, Gauss surface, it necessarily doesn't need to be spherical, okay? It can be any shape. It says imaginary. So what will be the flux proportional here? Do we have any charge inside the surface? There's no charge, right? So flux is zero in this case. In this case, flux is zero. So it's simple, right? I'll say, isn't it simple? Okay, we understood the Gauss theorem. We understood the Gauss theorem, but what is flux? What is this flux? So let's understand what's flux. To understand flux, I have a very simple analogy. Let's think this way. In a pipe, there's water flowing. There's a pipe and water is flowing through this. My question is, how much volume of water is flowing through this area? How much volume of water is flowing through this area? So from mechanics, you know that it is area into velocity. Okay, it's area into velocity. That will be the volume flux through that area. Okay. Now, what if I change the area? What if I increase the area? Or I increase the velocity? What will happen to the volume flux? What will happen to the volume flux? It will increase, right? Obviously, it's going to increase. So if I increase the area and if I increase the volume, it will increase. So similarly, what you can remember is flux is analogous to V dot. That means the volume flux. Flux is similar to volume flux. Area is similar to area and electric field strength is similar to velocity here. Okay. Just remember those two equations. They are very similar. And this is the same equation we have in magnetic field. So we know the equation that flux is equal EA. Okay. Flux is equal EA. If I change, if I increase the strength of the field, if I increase the strength of the field, then number of field lines through this will increase. Okay. Then flux will increase. Or without increasing the flux, what I can do is I can increase the area I consider. Maybe I can consider a larger area, something like this. Then also flux will increase. Okay. So we have to remember that if E or A changes, flux changes. Okay. So now we know that we have two equations for flux. We have two equations for flux. One is from Gauss theorem. The other one is from what we look now, EA. So, so far, is it clear what's happening? Do you understand what is flux and how you can remember that? And what are the two equations we have for flux? Okay, so what we are going to do is, when we are going to find the electric field, we are going to put these two equations together. We are going to get one of the equation from Gauss theorem and the other equation from flux is equal to EA. And then we are going to equate them. That's how we are going to find the electric field strength. Okay. So we have a small exercise to do over here. Let's start from conducting hollow sphere. Let's start from conducting hollow sphere. Okay. Now, this is the Gaussian surface I'm going to consider. This is the Gaussian surface I'm going to consider. I am free to choose any Gaussian surface, but what I have to do is I have to choose a surface such that uh, all the lines will be perpendicular. Okay, we have to get a field. I mean, we have to consider a surface such that all the field lines will be perpendicular. Is that clear what I'm saying? Did you get the idea why it should be perpendicular? Now, as we mentioned earlier, did you all get my question? Earlier, I said the surface would be any shape, right? I said this surface could be any shape. But now what I have done, I have selected uh, a spherical surface. Okay, I have selected a spherical surface. So what I have done, but here I have selected a spherical surface. Okay. Does anyone know the reason why? Why did I do that? The reason is now if you take a sphere, the charges are on the surface. If you provide charge, charges reside on the surface. Okay. And how is the field lines? Field lines are perpendicular to the surface. Field lines are perpendicular to the surface. So what I am doing is I have to consider a surface such that these electric field lines always will be perpendicular to the surface I consider. So the best surface I can consider is a sphere. Consider a surface where the field lines will be perpendicular to the surface. Is that idea clear? How about the others? You are free to choose any surface, but we are choosing a surface such that the field lines should be perpendicular to them. Okay. How about the others? Is it clear or shall I explain once again? Okay, what I said is now these field lines, look, when I said about the Gaussian surface, I said you can choose any shape. Okay, for Gaussian surface, you can choose any shape. But here, what I have done is I have taken a spherical surface. Okay, I have taken a spherical surface. So why did I do that? That's the question. Okay, why did I choose a spherical surface? Now, although we are free to choose any surface, what we have to do is we have to choose a surface where the field lines will be perpendicular to the surface. Okay. So for a sphere, if you want to choose a surface such that it is perpendicular, then it will be another spherical surface. Okay. Then just tell me, what about a slab? No, let's think about a cylinder. Okay, that's a good question. For a cube, then what type of surface? Okay, let's go for a simple one. Then let's go there. Now, just think about a wire, a long wire. Okay, we have a long wire. We have a infinite long wire. Now, this wire is infinite long. Okay, it's going till infinity, and this side also it's going till infinity. Now, there are charges on the surface. There are charges on the surface. Now, what type of surface is better for this? How about a spherical surface? Is it good? Is a spherical surface, does it suit for this one? What about having a spherical surface? Is that good or not? Then what type of surface is good for this? What type of surface is good for this? Yes, for this, to understand what type of surface is good, first we should know how the field lines are. Okay, so the field lines, if you draw the field lines will be perpendicular to the surface. So it will be in this direction. Okay, it will be in this direction, just like this. So it's perpendicular. So it's going into the screen as well as coming out of the screen, okay? I'm not drawing that. So what type of surface is good so that all these lines that is going into the screen just like this, those field lines that is going in, and the field lines that is coming out, we need a surface such that all these field lines are perpendicular. So what type of field line is better? Obviously, as you all said, a cylindrical one is better, right? If we choose a cylindrical one, then if we choose a cylindrical one, we can get the field lines perpendicular. So if I choose a cylindrical surface, then for this surface, this outer surface, those field lines become perpendicular. Is it clear? So be careful about that, okay? So you should know what type of surface to use when. Although you can use any surface, you have to be careful about what type of surface you choose. Okay, so let's fill this chart. Can you tell me what is the charge when R is less than A? How much charge is there? What is the enclosed charge when R is less than A? When R is less than A, that's no charge, right? It's no charge. Charge is zero because look, R is smaller than A. All the charges are, there's no charge inside this area. Okay, so charge is zero. If charge is zero, what can you tell about the flux? Flux is once again zero, right? Because flux is proportional to Q. Then what about the area? Area doesn't matter. Then what about the electric field? We know that electric field is Q over A epsilon naught. How did I get that? It's simple. We know that flux is equal flux is equal uh, Q over epsilon naught, and also it is equal to EA. So we are making a relation between the Gaussian theorem and the other equation we know. So we have to just subject E. If I subject E, Q is E is equal to A over epsilon naught. That is the equation we have over here. Okay. So what is E? E is zero. When R is equal to A, how much charge is there on the surface? When R is equal to A, how much charge is inside the surface? We have Q charge, right? We have capital Q charge. When R is equal to A, when R is equal to A, we have capital Q charge. Then how much is the flux? Flux is Q over epsilon naught. Okay. Then what is the area? Area is area of the sphere, 4 pi A square. Okay, 4 pi A square. Then what is the equation we get? We get E is equal 1 over 4 pi epsilon naught Q over A square. Okay. Okay. Now, when we take R is equal to A, that means we are considering the surface. Okay, we are considering the surface and the charges are on the surface. So we include that. Okay, it is not excluded. Is it clear? Those who said that's zero and had a doubt. So just remember that when we say R is equal to A, we have to include that charge, not exclude them. Okay. What if R is greater than A? What if R is greater than A? If you are considering an area just like this, how much charge is inside that area? How much charge is inside that area? Once again, Q, right? Then the flux is going to be Q over epsilon naught. And the area is going to be 4 pi R squared. And equation is going to be 1 over 4 pi epsilon naught Q over R squared. Okay. I hope you are okay so far. Is it clear how we got those equations? How about the others? Now, is there anything special about R is greater than A? Is there anything special about R is greater than A? R is equal or greater than A? Is there anything special? What do you all say? Is there anything special about R is greater than A? Have you noticed this equation? Have you seen this equation anywhere else? This equation, have you seen anywhere else? Anyone? How about the others? A few of them told the answer. Uh, so I'll go to the top of the slide. Okay, then you'll understand what I'm trying to tell. So just let's recall what we are doing. We actually started from here. Okay, we actually started from here. I said electric field, divide them into point charges and other charges. So these equations are only valid for point charges. Okay, these equations are only valid for point charges. And we finished that discussion. Okay, we finished that discussion. So point charges discussion Muniji. Then we came into other charges. Okay, we came into other charges. There we made a very important point. I said that Coulomb's law is not directly applicable. I said Coulomb's law is not applicable. But when we started discussing other charges, all of a sudden we have come to a similar equation. Okay, we know this equation. This equation is the equation for point charges. This is the equation for point charges, right? So that is special. That is special because I said for other charges, we cannot use Coulomb's expression, but at the end, we have got a similar equation. So what is special? This is special. And then I say, what we can do is, we can consider for R greater than or equal to A, conducting shell can be considered similar to a point charge. Do you understand what I'm saying? So whenever you get questions related to conducting spheres or some other spheres, okay, and if the radius is greater than the own radius, if the radius they're considering is greater than the own radius, then you can think that conducting sphere as a point charge. If it is less than, then only it is not. Okay. Does it make sense? Did everyone get the idea? If anyone has any doubts, let me know. I will clear that, because that's a very important thing. What I said now is very important. Anyone having any doubts? Okay, I'll repeat. I'll send the notes too. Okay, I'll send the notes at the end of this session, and I'll repeat. Ayan, are you okay with this? I mean, when R is less than A, I said electric field strength is 0. Okay, and when R is equal to A, we got this equation. When R is equal to A, and when R is greater than A, we got this equation. We got this equation. Okay, is that clear? The way we got that equation. So you're fine with that equation. What I'm saying is, although we got this equation for a conducting shell, actually we have seen that equation earlier. Where did we see it? We saw that equation when we discussed point charges. Okay, when we were discussing point charges, we saw that equation. So the claim I make is conducting shell can be considered similar to a point charge when R is greater than A. So let's say you have a question. Let's say you have a question. In a question, they are asking, there's a conducting shell. As a conducting shell, you place one more charge over here. Let's say this is 3 coulombs, and this is 5 coulombs. They want you to find, what is the force acting on this charge, okay, due to the sphere. So they have given this distance. They have given the radius, let's say that is A, and they have given this distance, let's say that is B. Then what is the equation for force? We know that F is equal, we cannot use Coulomb's law because this is not a point charge, right? This is not a point charge. This is not a point charge. Therefore, we cannot use the Coulomb's expression. But what I am doing, I am considering a distance. I am considering a distance that is greater than the radius. Okay, I am considering a distance that is greater than the radius. So, as I mentioned earlier, if we are considering a distance greater than A, then what we can do? We can say this setup is equivalent to a point charge of plus 3 coulombs placed at the center. And then we have another charge over here plus 5 coulombs. And now the separation is from here to here it is B, from here to here it is A. Did you get what I'm saying? Now you can apply F equal 1 over 4 epsilon Q over R squared, right? Did everyone get the idea? Now, if the question was, if you place the charge here, what's the force? We don't know. But because we are talking about a situation where the radius is greater, the distance is greater than the radius, we can consider this setup as a point charge placed at the center. Is it clear? So how about the others? Did I make sense? Have any doubts with that statement? Oh, fine. Okay. So now let's look about conducting solid sphere. Conducting solid sphere. Okay. I have a very important question. Where does the charge reside in a conductor? If you give a charge to a conductor, where does it reside? Does it store in the volume or on the surface? It will store on the surface, right? It will store on the surface for a conductor. If it is conducting, always the charge is on the surface. If it is on the surface, okay, if it is on the surface, um, can you tell me what is the charge enclosed if R is less than 0? Sorry, if R is less than A. If R is less than A, how much is the charge? If R is less than A, how much is the charge? 0. Okay. If R is equal to A, how much is the charge? You will have the complete charge. If R is greater than A, how much is the charge? That is also once again Q. Okay. Now, conducting solid sphere and conducting hollow sphere, do they have the same characteristics or different? Are they same or different? They are the same. Okay, they are the same. Yes, if it is insulating, it is inside. If it is conducting, it's on the surface. Okay. Atif, is it clear that they are the same? They are not different. Look, if R is less than A, if R is less than A, then it is 0. I mean, charge is 0. Here also, if R is less than A, charge is 0. R is equal to A, charge is Q. R is equal to A, charge is Q. R is greater than A, then charge is Q. R is greater than A, charge is Q. So they have the same properties, right? Therefore, what we can say is, now let's say you get a question. You are getting a question combining hollow sphere or solid sphere, but they are conducting. That means, are they same or different? They will have the same characteristics. Do you get it? So what you can do is, you can consider them as the same thing. They are not two different things. Okay? Does it make sense? Now, let's look at non-conducting, okay? Non-conducting thin hollow sphere. Non-conducting thin hollow sphere. Now, this time, Uh, Rimza, here we are not going to get any induced charge, okay? Because the charges are not able to go inside. So to have induced charge, we will need to have concentric spheres. We will need to have sphere inside a sphere. Then only we can have induced charges. Because we are only having one sphere, we won't have induced charge. Is it clear? Okay. So when we have a conducting thin hollow sphere, are there any differences in the charge distribution or the same? What's your answer? Is it same or different? The charge distribution. So I'm using non-conducting thin hollow sphere. So that means uh, what I am trying to tell, the charges are on the surface, right? I'm trying to express that the charges are on the surface. That's why I'm using this amount of words. Non-conducting thin hollow sphere. Okay. So the charge, any difference in the charge distribution? No, they are the same. Look, if R is less than A, if R is less than A, do we have any charge inside that? No, right? If R is equal to A, okay, so Nahla, what I'm doing is I'm saying it is thin hollow sphere. Hollow sphere means it doesn't have a volume inside. It only has an outer surface. Clear? How about the others? So read this statement and see if you can understand what's the conclusion I want to make. Those who understood this, put the thumbs up. The final conclusion that I made. How about the others? Okay with the statement. I say that conducting hollow and solid sphere. So conducting hollow and solid, okay, put them together. They will always um, have the same characteristics, okay. Then we have non-conducting. This is special. Non-conducting thin hollow sphere is identical to a point charge for R is greater than A. For R is greater than A, it is identical to a point charge. Okay. Shall we try these questions? Let's try from 23. Let's try question number 23. So a hollow sphere of copper. Copper means it's a conductor, right? Charge will be distributed over the surface. The electric field inside the sphere is zero because as we discussed earlier, there will be no charge inside that. Okay, according to the Gauss theorem, the charge enclosed is zero. Therefore, it will be zero. Try the next question. What about the boys? Are you all clear? So question number 33, surface of the hollow metal sphere increases. So once again, it doesn't matter, right? Even if we increase, now we have a surface. On the surface, even though I increase the charge, doesn't matter. Inside, there's no charge at all. Even if I increase, there's no charge at the center. Okay, therefore, it will be 0. Try 38. The answer should be D, right? Because, let me draw the diagram. We have a large isolated metal sphere of radius r carries a fixed charge. So we have a large sphere of radius r that is carrying a charge. So radius is r. Thus a small charge from the surface at a distance of s. So we want to find what is the force it experiences. Okay, we want to find what is the force it experiences. To find the force it experiences, now we have a solid sphere, right? It's hard to discuss. So what we can do is, as the distance I'm considering is greater than the radius, I can replace this sphere with a point charge at the center. Okay, I can replace this with a point charge at the center. So from the center to the surface, it is distance r. From the surface to the other charge, it is distance s. Then the force, we know it is proportional, inversely proportional to distance, right? It is inversely proportional to the distance. But the distance is now r plus s, whole thing squared. Okay, so it should be answer number D. Is it clear? Okay, so we can come to a very important conclusion now. If we have a solid sphere, hollow sphere, and they are conducting, then it is identical to a point charge for r is greater than a. Okay, it is identical to a point charge for r is greater than a. So far, what did we derive? We got the equation for E, right? We know how to find E. Can you tell me what is the equation for V? What is the equation for V? What is the equation for V for r is greater than or equal to a? Is it the equation of point charge or not? Is it the equation of point charge or not for r is greater than a? It's same as the point charge or different? It should be same, right? Because what did we say? For r is greater than a, for r is greater than a, it is identical to point charge. Okay, for r is greater than a, it is identical to point charge. That means for r is greater than or equal to a, for r is greater than or equal to a, v is equal to 1 over 4 pi epsilon naught q over r. Does it make sense? Are you clear with what I am saying here? So look, although we said that point charge equation is not valid for other types of charges, for some situation it is valid, right? So that is what you have to understand. Under which condition those equations are valid. If you understood that properly, then you can easily do these questions. Okay. Okay. Now what we have done is we have found VP for R is greater than A. But what about R is less than A? What about for R is less than A? That is where we are going to use the second tool. Remember, we said we would be using the potential gradient to find the potential. That's what we are going to do. We are going to use the potential gradient. We know E is equal delta V over delta X. And what's the electric field strength inside those spheres, conducting and non-conducting spheres? It is zero, right? It is zero. So we are equating delta V over delta X to zero. Okay, we are equating delta V over delta X to zero. So what is delta V? Delta V means not the potential. It is the change in potential. Okay, don't get confused. This is the change in potential. So we already know the potential on the surface. We already know the potential on the surface. Okay. So what we can tell is the potential difference between the surface and inside is zero. There's no change in the potential. That means potential on the surface, a potential inside is equal to potential on the surface. And that is 1 over 4 pi epsilon q over r. Is it clear how we got that equation? So what you have to understand is how this deriving thing comes from Gauss theorem, how we got the equations, and how we can, under what condition we can say that these spheres and point charges are similar. You should understand those concepts properly and how to find this potential. Okay. I will clear so far. Shall we look non-conducting solid spheres? Anyone has any doubts from the previous part? Now, y'all cannot remember everything what I said. What I'll do is I'll give the notes, the notes I have taken, so you can refer that later. But I'll clear with what I said so far. I mean, the last thing I said, how to find the potential. Is that clear, boys and the girls? Great. Okay, so now let's move on to non-conducting spheres, non-conducting solid sphere, non-conducting solid sphere, non-conducting solid sphere. Where does this charge reside? Does the charge reside on the surface or in the volume? Now the charges are stored in the volume. Okay, now the charges are stored in the volume. So let's start from R is equal to A. How much charge is there in R is equal to A? If R is equal to A, what is the charge? Q, right? Charge is Q. Then this is going to be Q over epsilon naught. Area is 4 pi a squared. Then E is equal 1 over 4 pi epsilon naught Q over a squared. Okay. What about R is greater than A? How much charge is there when R is greater than A? When R is greater than A, once again, we have Q charge. Therefore, flux is Q over epsilon naught. Area is 4 pi R squared. Then flux is, sorry, E is 1 over 4 pi epsilon naught Q over R squared. So, what can you tell? For R is greater than or equal to A, can I consider this as a point charge or not? For R is greater than A, can I consider this is similar to a point charge or not? We can, right? So it's really great that all those conducting spheres, non-conducting spheres, for R is greater than or equal to A, you can consider them as point charges. Okay. So whenever you come across a question, doesn't matter any question, if they are talking about the radius or the distance greater than its own radius, then without doubt, you can consider them as point charges. So is that concept clear? Now, whenever you see a sphere, conducting sphere question, you have to be happy that if R is greater than A, question becomes simple because that is going to be the trick. They are going to expect you to think that as a point charge. If you can understand that it's a point charge, then the question should become simpler. How about the others? Do you get the idea? Okay, what about R is less than A? What about R is less than A? Is the charge zero or not? What about the boys? What do you all say? Is it zero or not? Yes, it's not zero, right? It is not equal to zero. If it is not equal to zero, then the flux is not zero. If the flux is not zero, then E is not zero. So for a non-conducting solid sphere, E inside is not equal to zero. Okay. And we can prove that E is proportional to R. We can prove that E is proportional to R. Okay. Uh, you can refer the notes for that to, I'm not going to prove it. I'm just telling that A is proportional to R. And you don't need to worry about the equation for V because deriving it is complex. So we are not going to get a question from that. But you have to remember the graphs. You have to remember the graphs. I'll just quickly draw the graph. It is something like this. Okay. And if you draw the V versus R, you draw the V versus R, it is something like this. V versus R and V versus R. So you can refer the notes for that. But what I want you all to understand is that E is not zero. Hope it's clear. Did you get the idea? So I hope from the discussion so far, you understood how to use, you understood that point charges are different and other systems are different. And you cannot directly use the Coulomb's laws. Here, they are not valid. Okay. What we have to do is we have to use Gauss theorem to get the equation for E. And we can use other potential gradient delta V over delta X to find the potential. Okay. So I have shown how to get the equation for spheres. I have shown how to get the equation for spheres. Conducting, non-conducting, hollow, solid, all those types of spheres. Now you can refer the notes for others. What I want you all to understand is why we need the Gauss theorem and how we use the potential gradient. What do you all think? Was I successful in explaining that? The Gauss theorem ye theva, potential gradient ye theva. Idu rendeyum clear avaniyera. Did you all get an overall picture of how this fields unit is structured? Point charge is different and all the system is different, and how to derive the equations. Why are clear so far? Then let's look at some general equations that we can use for any charge system. Okay, we can use for any of them. If it is a point charge, or doesn't matter if it's other types of system, whatever type of system, these equations are valid. Okay, just like in waves and oscillation, velocity is f lambda. Any wave, it will obey, right? For any wave, this will obey. V is equal to f lambda holds. It works. Just like that, in electric field, we have a few equations that is valid for any system. Doesn't matter whether if it's a uniform electric field, non-uniform electric field, point charges, whatever, these equations work. F equal EQ. E is equal to delta V over delta X. Q is equal to CV and W is equal to QV. So these equations you can use for any systems. So when you try questions, if it's not a point charge, when you read a question, you must understand if that question is related to point charge or not. If it is not related to point charges, then you will go with these equations. Okay, because these are general equations. You can use for any of them. Okay, this potential gradient equation, why are we having this negative sign? This negative sign actually shows the direction. Okay, this shows the direction. So the proper equation is delta V over delta X. And if you want the value only, put the modulus. Then you can just get rid of that negative. Okay, if you want the magnitude only. Okay, so there are some commonly misunderstood ideas. Okay, let's check them. And I think that's the end of the section I want to discuss. Now, I have a question. Let's say we have two charges, Q1 and Q2. We have two charges, Q1 and Q2. We know that thus a little amount of energy stored between them. Thus energy stored between them. My question is, where is the energy stored? Where is the energy stored? Are they stored in each charges separately? Some portion is stored in Q1 and some portion is stored in Q2. Is that the case? Is it like that? What do you all say? Simple answer. Yes or no? I'm not going to ask questions, okay? Just, you have to just tell yes or no. just to let understand your idea. Some energy is stored in Q1, some is stored in Q2. Okay, I am getting answers. What about the others? What others say? Are they stored in between Q1? Sorry, some energy is stored in Q1 and some is stored in Q2. Yes, what about the others? Some say no. Few say no. Some say yes. Some say yes. Okay. Okay. Yes is overtaking no. Now I have more yeses than nos. Let's see. Now let's think about this atom. I mean this molecule. You know this, right? Sodium chloride, NaCl. Sodium chloride, it's a positive charge and a negative charge. Okay. So they have attractions. They are attracted. And my question is, where is the energy stored? Chemistry students, chemists, you all know that, right? That energy between sodium and chlorine is stored in ionic bond. Okay, they are stored in ionic bond. So none of the energy is stored in sodium or chlorine. They are stored in between them. Okay, energy is stored in between them. Do you get what I'm saying? It is clear that energy is stored between charges, not on a single charge. So the answer should be no. I all clear? Or should I repeat? Those who said yes and those who said no as well, I all clear that the energy is not stored in one of them. Actually, they are stored between them. So I can tell you an example. Now say, if you move Q1 behind, then the energy will increase. Okay. And let's say you move Q1 behind, then also energy will increase. So we can understand that the energy is between them, not in one of them. So it's here in the bond. How about the others? Did you get the idea? Most of you answered yes. So the answer is no. And did you get the idea? நிறைய பேர் எஸ்ன்னு சொன்னீங்க அந்த ஆன்சர் வந்து நோ இப்போ நினைச்ச ஐடியா those who said yes. Okay, let's look at this example. Can you tell me where the energy is stored? Here in this system, where's the energy stored? If you want to find the energy of the system, what you have to do is you have to calculate the energy between A and B. You have to calculate the energy between A and B. Plus, you have to calculate the energy between B and C. And then you have to calculate the energy between C and A. Is that clear what I'm saying? As I mentioned earlier, the energy will be stored between, okay, between. So you can have energy between A and B. You can have energy between A and C. Then you can have energy between B and C. I think I have considered all the possible bonds. So the energy of the system is the energy on these three bonds. Does it make sense? So they are point charges, right? Then the equation is 1 over 4 pi epsilon naught Q1 Q2 over A. Let's say this is A plus B and C, right? That is Q2 Q3 Q2 Q3 over A plus next C and A Q3 Q1 over A. That is the equation. You can find the answer. Do you understand how I wrote that equation? Shall we check next? Do you get it? Or shall I repeat? Most of you got silent. No answers yet. Understood or shall I repeat? Okay, I'll repeat. As we discussed earlier, uh, the energy is stored in the bonds. Okay. Oops. The energy is stored in the bond. So what I'm looking is what are the possible bonds here? What are the possible bonds we can have? We can have a bond between charge Q1 and Q2. That's that bond. Okay. Yeah, I'm talking about the potential energy. So this bond, okay, we can have a bond between A and B. Then we can have a bond between A and C. So I think I have considered all the possibilities of A. A has a bond with B, A has a bond with C. That's all. Next, let's go to B. If I go to B, what are the bonds B has? B has a bond with A, which I have already considered. Next, B has a bond with C. I have to consider. I considered now. So I'm done with B. Now let me go to C. If I go to C, C has a bond with A. I have already considered. C has a bond with B. I have already considered. Therefore, we only have to consider three bonds. That's what I have written here. Energy between A and B, energy between B and C, energy between C and A. Ayan, is it clear? Then equation is 1 over 4 pi epsilon naught Q1 Q2 over R. If you cannot remember the equation, you can check the note. The equation is Q1 Q2 over R. The separation, that is A. That is for B, A and B. Next, if we consider B and C, that is Q2 Q3. Q2 Q3 over A plus if we consider C and A, that is Q3 and Q1 over A. Is it clear how I got the equation? Okay, good. Now let's try this. Can you tell me, I mean, just like this, okay? Here I have written E, A, B, B, C, just like that. Uh, can you send me a message? What's the energy of the system between who should I consider? Yeah, I think I got one answer. Others? Okay, we got two answers. So you can just mention between what and what, okay? A, B, C, C, D, A, B. Zainab, I think you're missing a few. B, C, C, D, A, B, B, C, D, E. Okay, we got three. How about the others? So let's check. First, I'll start from A. If I look at A, okay, if I start from A has a bond with B. And also, even though I have not drawn it, but A has a relation with C. Okay, so A has a relation with C. Next, A has a relation with D. Okay, now let's go to B. If I go to B, um, B and A I have considered. Although we have not drawn B and D, still there's a relation between B and D. B and A is okay. B and D I have to draw. Then I have a bond here. Okay. Next, B and C. That's fine. Now let's go to C. If we go to C, C and B is already considered. C and B is already considered. C and A is also already considered. C and D should be considered. So let me consider C and D. So this is also considered now. Now let me go to D. If I go to D, D and C is considered, D and B is considered, D and A is considered. So D is also done. Then it should be energy of A and B plus energy between um, B and C plus energy between C and D plus energy between D and A plus energy between, now what I have done is I have considered this, this and this. Okay, I have to consider A and C plus B and D. Is it clear? How about the others? Any doubts? How about the boys? Are you all clear? So uh, soon after this section, you have capacitors. Capacitors, probably you should have a good idea how to solve them. So I didn't include that in the note. And there's one more part, that's concentric spheres and electromagnetic induction. Induction and concentric spheres. Okay. That part I have not included here because if I do everything together, it's going to become a mess. So in today's session, this is what I wanted to discuss. I'll just recall what we did so far. Uh, to tell in short, what I did was we started electric field. Then we understood that electric field equations that we know, the Coulomb's expressions, that is actually defined for point charges. Okay, that is actually defined for point charges. And for other systems, we had to use Gauss theorem. We had to use the Gauss law, and we had to use the potential gradient equation to find the equations for E and V. Okay, we get the equation for E and V. We had to use other techniques. And when we did that, we discussed especially for spheres, okay? We specially discussed about spheres today. In that, we came to a conclusion that for a sphere, if we are considering distance that is greater than or equal to its radius, then this is similar to point charge. Okay, this is similar to point charge. When it is less than A, then only we have different conditions. Even in this condition, if it is conducting, E was 0 and V was equal to V surface. If it is non-conducting and solid, then E is not equal to 0 and V is also something else. V is greater than V surface. Okay. At the center, V is greater than V surface. So I gave the idea about how to use the Gauss law, how to consider a surface so that you can easily refer your notes. So you're going to refer your notes to get a better understanding about the other sections. Okay. So that's the brief of what we discussed today. I hope you all understood the concepts. Was it clear? Was the today's workshop successful? Did it achieve its objective? So what you have to do is you have to go through those electric field questions. I think I have already shared. And for most of them, I have shared the explanations too. So what you can do is you can try those questions, go through those explanation and get a better understanding so that you can prepare for the exams. Okay, so I hope to have the exams by the end of this month. Then all the best for the exams. I'll upload the recording to a drive or something, and if you all need, you can get it. Okay. Jazakallah for joining and participating actively and very enthusiastically. I have to say, most of you were really engaging, so it was really interesting for me too. So, Jazakallah khair for joining. Let's end the session. Assalamu alaikum.